Hi everyone, Mrs. Hanson once again. Hey, we're going to pick up some lessons with Lewis dot structures in 4.2, beginning with the definition of a molecular formula. Once and again, we know that it shows the number and identity of all the atoms in a compound. But what it lacks really is just not showing us the connectivity of how the atoms are bonded to one another. So for example, if I were to tell you we had a molecular formula of C2H6, you would know that there are 2 carbons and 2 hydrogens in that molecule, but you really wouldn't know how they're connected together. And that's a huge advantage when we see a Lewis structure, because now it's going to show us the connectivity between the atoms, as well as all of those bonding and non-bonding valence electrons. That when I start to see the carbons connected together, and that each carbon is going to complete its 4 bond requirement by placing all of those hydrogens attached to it, we now can see a Lewis structure for the molecule, knowing that I see a carbon to carbon single bond, and I notice that each carbon has 3 hydrogens attached to it. And so that's the advantage really of a Lewis structure, is showing connectivity. What we also will involve ourselves with, and just kind of thinking about what's coming here, we're going to be involved in the Vesper theory in a few sections from now, in which we start thinking about molecules as these 3-dimensional objects. In addition to how they're connected, we'll get an idea of what their geometry is as well. And that we'll learn that a carbon with its 4 bonds will have a molecular geometry known as tetrahedral. Tetrahedral is not spelled right. I'll just say it, tetrahedral. And you'll have an idea that it looks like a tetrahedron with bond angles of 109.5, all coming our way as we begin. But, first steps, let's go through these guidelines for drawing Lewis structures. How do I create a Lewis structure? And then we're going to practice in this section. So, first step in creating a Lewis dot structure is to count up how many total number of valence electrons we have in a compound. And what I mean by that is, a moment ago we drew methane, CH4. I know that carbon, who lives in group 4A, has 4 valence electrons. I know that hydrogen, who lives in group 1A, has 1 valence electron. But knowing that there's 4 hydrogens in the compound, I know that there'd be 4 total dots, if you will, coming from hydrogen. There would be 8 valence electrons in a methane molecule. Count up the total number of valence electrons. How many dots do we get to play with? Number 2 says we're going to select a central atom, which is always the least electronegative element. Now, we have yet to define electronegativity, but I can just share with you, it's the ability of an atom to draw electrons towards itself in a shared pair, in a bond. Fluorine, we'll know, is the most electronegative element. It's the strongest of strong nonmetal. And because fluorine is in the top right of our periodic table, the least electronegative would be the furthest away. And we said never put hydrogen or a halogen in the center because it only gets 1 bond. And since we have to attach all of these atoms back to the central atom, don't pick an atom to be the central. It only has 1 bonding opportunity. We'll then learn to connect back all the other atoms to the central atom using a single bond. And as we practice, we'll say, okay, carbon will be in the center, and I'm going to attach back all of the other atoms to the central atom. Never, ever start creating these linear attachments, right? It just doesn't work that way. Instead, we attach back to a central atom, and we always think symmetry. Let symmetry guide you through your selections. After we connect back to the central atom, we're going to fill the octet of all of those outer atoms, again, tallying the electrons. If we run out to fill the central atom, we kind of consider a double bond or a multiple bond. And I wanted to do some examples with you just so that you can look at these rules and actually employ them. And the first one we did was methane, CH4. But let me go through that step by step again. Step 1, tally your electrons. And what I mean by that is how many dots do we get to play with? right? How many dots, no more nor less, do I have to make my molecule with? We said since carbon lives in group 4A, it's going to have 4 valence electrons. Since hydrogen lives in group 1A, we have 1 valence electron, but there's a total of 4 hydrogens in the compound, so 4 dots. That means we get 8 electrons total to build our molecule, step 1. Step 2 said, select the least electronegative element, the farthest from fluorine, and put it in the center. Well, here, if we're not allowed to use hydrogen, clearly we see carbon is in the center. Next thing I do is attach back all of the other atoms, which are all 4 hydrogens, to the central atom, and then retally. Remember, each shared pair is 2 electrons, so we used 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons were done. Now what's nice is with this very first simple example, we drew a molecule that very quite simply satisfied the octet. I ran out of electrons, all done. So with our methane molecule, we'll learn that the carbon attached to those 4 hydrogens has a molecular geometry known as tetrahedral. And that those bond angles are going to be 109.5 degrees away from each other. A tetrahedral atom, not a 90 degree like our Lewis dot structure suggests, but a carbon attached to 4 other atoms is a tetrahedral shape. Let's consider a next example, and I'll just work down the page there with those examples for you. Notice the next one on your worksheet says PCl3. Phosphorus Trichloride. Let's count how many total electrons we have. So tally your electrons. Phosphorus, who lives in group 5A, it's going to be able to contribute 5 electrons, 5 dots in my structure. Chlorine, who lives in group 7A, contributes 7 valence electrons. But do you see how there's 3 of them in the formula? So the total number of dots, total number of electrons from chlorine will be 21. When I sum those, I get 26 electrons to play with. No more, no less, I get 26. Step 2 says, select a central atom and place it in the center. Select your central atom. Never pick a halogen like chlorine because it only has room for 1 bond and you run out of stuff to do with it quickly. Phosphorus is the least electronegative. And so when we get this far and define electronegativity, we want to define electronegativity as the ability to draw electrons towards itself the atom's ability to draw electron towards itself in a covalent bond. So we want the least electronegative element, the farthest from fluorine, the least likely to be able to pull electron density towards itself. And clearly you can see that that's phosphorus. Phosphorus will go in the center. And I'll tell you, instinctively, you're always going to know to be able to pick, just think symmetrical. Symmetry, phosphorus in the center, and I can see attachments of chlorines going back. Step 2, we selected the least electronegative element, so we have the central atom. Step number 3, attach back all of the other atoms. So when I do that, when I attach back, that's chlorine, chlorine, chlorine. Those are the 3 chlorines. I attach them back. And remember to retally. We had 26 electrons we were working with, right? That's what we tallied up here. To create 3 single bonds, we used 1, 2, 3, 4, 5, 6. That leaves us 20 electrons left to place. Step 4, complete the octet of all outer atoms. One, 2, 3, 4, 5, 6, he's done. 7, 8, 9, 10, 11, 12, he's done. 13, 14, 15, 16, 17, 18, he's done. We used 18 electrons to complete the octet of the outer atoms of chlorine. That leaves us 2 more. And that last step says, complete the octet of the central atom. Those 2 get placed on the phosphorus. We've used up out of dots. And we've recognized that all of those atoms now have an octet. Here, the phosphorus, 8 valence electrons. Each chlorine, 8 valence electrons, with 3 single covalent bonds, each now with 8 electrons around it. Phosphorus trichloride will learn. The name PCl3 will learn phosphorus trichloride. Hear the "ide" on the ending? That's coming up in our lessons, how to name these babies. And then we'll also learn that since phosphorus in the central atom has attachments to 3 atoms and 1 lone pair, so just to highlight, it has 1 lone pair and attached to 3 atoms. We'll learn to use our VSEPR chart, valence shell electron pair repulsion, to find its molecular geometry, and we'll learn to call this trigonal pyramidal. And that it really doesn't look like those right angles I drew, that the phosphorus with its lone pair will have a chlorine coming down, a chlorine kind of coming out of the page at you, and a chlorine kind of coming behind the page at you there. And you'll learn that we'll think about these in a 3-dimensional object where those chlorines are the base of a pyramid. What's next to draw? We're going to look at CH5N. All right, CH5N. That's our next example. So this is interesting. We've got CH5N. Again, a molecular formula tells us how many of each we have, but no idea of connectivity. This time when I select the central atom, the least electronegative element, the furthest from fluorine, electronegative, we kind of have to think about who's going to be the central atom. And I know I have to tally the electrons. Just kind of brainstorming my approach. All right. Carbon lives in group 4A. It will contribute 4 dots. Hydrogen lives in group 1A. It contributes 1 dot. But there's 5 of them in the structure, so I'll get a total of 5 dots contributing from the hydrogen. And of course, nitrogen lives in group 5A. So let's add what we have. We get 4, 9, 4. This adds to 14 electrons, 14 dots to build our structure. Alrighty. So thinking about what we know about atoms, I know that carbon is allowed to have 4 bonds. I know that. I know that carbon lives in group 4A. It has room for 4 dots. Alrighty. I also know that nitrogen, who lives in group 5A, will have 1 lone pair and room for 3 bonds. And then hydrogens are always just used as kind of attached back at the end to fill octets, right? It's only allowed 1 bond. So that's what I'm thinking about as I decide how to connect my atoms together. It makes no sense to put a hydrogen in the center because it cannot have two bonds. I'm not allowed to do that. So it can only go on the outsides of the structure. But what I can do is connect a carbon and a nitrogen and still meet the requirements of how many bonds and how many lone dots it's allowed to have. So thinking that through, when I placed carbon next to nitrogen, I did so because I knew that a hydrogen could not be attached between the two elements. Let's retabulate how many things we've used. We've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 dots. And something magical has happened. We're allowed to just place all of those hydrogens leading to those, leading out from those single bonds, and we've used all 14 electrons. We've satisfied the octet. We've used the hydrogens as like the outside atoms to complete the bond requirements. And really what we let guide us is the discovery that carbon needs 4 bonds, that hydrogen needs 3 bonds and 1 lone pair, and that hydrogen is only allowed 1 bond as it's completing its octet. And we assembled those pieces to create a Lewis dot structure. This will also kind of be fun. We'll talk about the geometry around each particular atom, that we only focus our attention to one central atom at a time when we talk about molecular geometry. We'll learn that since this carbon is attached to 4 atoms, attached to 4 atoms makes it a tetrahedral molecular geometry. We don't know that yet, but we're going to, tetrahedral. And that this nitrogen is attached to 3 atoms and 1 lone pair, so we're learning that that's called trigonal pyramidal. So we have 2 central atoms in that molecule. Let's turn our attention then to the right side of your examples. We've done CH4, we've done PCl3, and we just did CH5N. How about HCN, hydrogen cyanide? Hydrocyanic acid is another word for that. All right, let's tally our electrons. Hydrogen lives in group 1, 1 valence electron. Carbon lives in group 4. Nitrogen lives in group 5. We have just 1 atom of each. That gives us 10 electrons. The least electronegative element will go in the center. That's carbon. We'll attach back all of the other atoms to the central atom. So the carbon is in the center, leading out to nitrogen in one direction, hydrogen to the other. That took a total of 4 dots, right? Because each bond is a pair of electrons. That leaves us 6 electrons. Then the rule says fill the octet of all the outer electrons for all the outer atoms first. Hydrogen never gets any dots. So the 6 electrons go around the nitrogen. And we're out of dots then, aren't we? Clearly you see that the carbon is not yet satisfied. It needs to have 4 bonds. Nitrogen is fine with its, you can see that it has 3 sets of dots and 1 bond. But do you remember what we've learned? Carbon needs 4 bonds. Nitrogen needs 1 set of dots and 3 bonds. Right now our structure is not yet complete. If we were to take 2 sets of dots from nitrogen and bring them together into a shared pair between the between the carbon and nitrogen, we can satisfy the bond requirements of both atoms. If we run out of dots, the direction said, consider a multiple bond. And when you do so, when you consider the multiple bond, we've now got the arrangement of those atoms exactly like we want. In other words, this carbon has the 4 bonds that it requires. One of them is a triple bond, and the other is a single, but that still adds to 4 bonds that it requires. The nitrogen needed 3 bonds and a set of dots. It has exactly what it wants. 3 bonds, all involved in a triple bond, still counts as 3 bond requirements and 1 lone pair. We just drew HCN with a triple bond leading out to the nitrogen there. HCN. Let's keep going. This is fun. Carbon lives in group 4A. We have 4 valence electrons. Oxygen lives in group 6A, and there's 2 of them, so we get a total of 12 dots. Then 16 is the sum, 16 dots, no more, no less. The least electronegative element is carbon. It will go in the center. The furthest from fluorine is carbon. I'm going to attach back all of the other atoms to the central atom using single bonds. To do that, we used 1, 2, 3, 4 dots because those are shared pairs. We have 12 dots remaining. Now that says, fill the octet of all of the outer atoms next. We used 12 dots to fill the oxygens. We're out of dots. When you run out of dots and the central atom has not yet achieved a noble gas configuration, consider a multiple bond. In other words, we know carbon wants to have 4 bonds. We know oxygen wants to have 2 bonds and 2 sets of dots. So we get a feel that we're just not done yet. Now I can move a set of dots between each side of the carbon and a shared pair where oxygen is leading to a double bond leading out to the next oxygen. We've met the requirement for each atom. Carbon, 4 bonds, just like it wants to have, involved in double bonds in both directions. The oxygen, 2 sets of dots, 2 bonds, perfect. Oxygen, 2 sets of dots, 2 bonds, perfect. Carbon dioxide places carbon in the center with 2 double bonds in each direction to the oxygen. We'll try another together, CH2O. Carbon lives in group 4A. It's going to contribute 4 electrons. Hydrogen lives in group 1A. Each one of those hydrogens contributes an electron. We'll have 2 coming from hydrogen. And then oxygen, of course, in group 6A has 6 valence electrons. That's 6 and 6, that makes 12 dots. No more, no less, we get to use 12 valence electrons. The least electronegative element goes in the center. Now remember what that means? That's carbon, the farthest from fluorine. Carbon is further from fluorine, so it is least electronegative. That term we'll learn just means the ability to draw electrons towards itself in a shared pair. Fluorine is the strongest of strong nonmetals, pulling electron density towards itself. The farther you move away from fluorine, the weaker the atom becomes at drawing electrons towards itself. Carbon is farther from fluorine than oxygen. That's how I know carbon will be the central atom. We attach back all of the other atoms to the central atom using single bonds. To do that, we used 6 electrons. Remembering, each shared pair is 2 electrons. We have 6 dots left. Fill the octet of all of the outer atoms. That's the oxygen. Hydrogen never gets dots, so we'll fill the oxygen next. We're out of dots. However, clearly we see oxygen wants to have 2 dots, 2 bonds. That's what it would like to have. Carbon needs to have 4 bonds, so we're not done yet. Do you notice carbon doesn't have enough bonds? So when we run out of dots and the central atom has not yet reached its 8 electrons, that's when you're told to consider the multiple bond. We can take the set of electrons from oxygen and give them to carbon in a shared pair. Now we've achieved 4 bonds around the carbon just like it wants to have. We've achieved each hydrogen's 1 bond just like it wants to have. And we've achieved the oxygen 2 dots, 2 bonds. When I redraw this clean, we'll see that since carbon is attached to 3 atoms, it's attached to an oxygen, it's attached to a hydrogen, it's attached to a hydrogen. That central atom carbon is attached to 3 atoms, that the molecular geometry is now called trigonal planar. It's going to look like an equilateral triangle. We'll learn that when we get to the Vesper theory section of our chapter, we'll see that this truly is an equilateral triangle around the central atom. Equilateral triangles have bond angles of 120 degrees, right? So as I think about the bond angle between the hydrogens, the bond angles between the oxygen, all of those looking like an equilateral triangle. So I'm integrating all kinds of good stuff as we practice. The Vesper theory, bond angles, how to draw Lewis dot structures, kind of being real sneaky and teaching you everything at once so that as we practice, it will become quite easy. It's time for you to practice. Turn off the video for a minute, draw these molecules, come back and compare with me. Don't cheat yourself of the opportunity. It's so important for you to try first, then come back when ready. All right, let's come back. Letter A, HBr. You noted that hydrogen with its 1 valence electron, bromine with its 7 valence electrons, you knew you had 8 to do, 8 dots to do. And this one was so easy. 1 single covalent bond, and you had the formula for HBr. In letter B, CH3F. Carbon contributes 4 valence electrons. There's 3 hydrogens for a total of 3, and fluorine, the halogen, will contribute 7. That gives us 14 dots by the time we're done drawing. You picked the least electronegative element to be the central atom. Never pick hydrogen, never pick a halogen. And you attached back all of the other atoms to the carbon. And when you did so, you tallied that you used 8 electrons to make 4 single covalent bonds, leaving you 6 dots left. And then I'm sure you placed those 6 dots around the fluorine. All done. Letter C, H2O2. Hydrogen each contributes 1 electron, but there's 2 of them. Oxygen contributes 6 electrons, and there's 2 of them. That gave you 14 dots altogether. Knowing that we cannot place a hydrogen between 2 atoms makes no sense because hydrogen can only have 1 bond. You didn't fall for that. You knew that the oxygens would have to be connected together. That an oxygen connected to a next oxygen, and then you would attach back, always thinking symmetry. Hydrogen can only have 1 bond, so that made them go on each side of the oxygen. There's your H2O2 using all 14 electrons. Oxygen, 2 sets of dots, 2 bonds, just like it wanted to have. I'm going to clean that up. 1 bond, 1, 2, 3, 4. There, we got it. So just to emphasize, we know oxygen wants to have 2 bonds, 2 dots. 2 bonds, 2 dots, and each hydrogen now has its 1 bond that it has. Perfect, I'm sure you're doing great. Let's look at D. N2H4. Nitrogen lives in group 5A, so we know it's going to contribute 5 dots for a total of 10. Hydrogen with its 1 valence electron contributing a total of 4. We get 14 dots. We know that the nitrogens need to connect to each other Because we know that hydrogens cannot have more than one bond. So just by connecting them together, we've used 2 dots. Alrighty, now we have 4 hydrogens. So let's remember too, what we're trying to say is nitrogen needs to have 3 bonds and 1 set of dots. That's what it wants to have. So as I think about attaching the hydrogens, think symmetry. I'm going to place them evenly so that you see that nitrogen each received 2 hydrogen. And what did we use? We used 1, 2, 3, 4, 5, 6, 7, 8, leaving us 4 electrons left. 1, 2, 3, 4. Each nitrogen has its 3 bonds and 1 set of dots. Each nitrogen, 3 bonds, 1 set of dots. You drew the Lewis dot structure, connecting the nitrogens together and using the hydrogens to complete the bond requirement. C2H6 came next. Yep, C2H6. We know that carbon has a 4 bond requirement. We know that hydrogen can never be, it makes no sense to try to put a hydrogen between a carbon because there's too many bonds there. So you must connect the carbons together. Carbons with its 4 bond requirement, I'll take the hydrogens to complete each of those carbons 4 bonds, and we've got it. There's C2H6. And letter F gave us CH2Cl. 2 hydrogens, 2 chlorines. The least electronegative element, carbon. Never put hydrogen, never put a halogen. I'm going to satisfy the carbon bonds by placing all of those around, remembering to complete the octet with all of those electrons that chlorine requires. Remember, carbon has 4 valence electrons. Hydrogen will contribute 1, but there's 2 of them together. Chlorine has 7 valence electrons, giving us a total of 14 dots. That gave us 20 dots to make our structure. 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10, 11, 12, 13, 14, 15, 16, 17, 19, 20. Hey, we used them all creating our dots. I hope that's getting easier and easier. You know, a next set of problem I wanted to look at with you coming from your homework, where they give you kind of an attachment idea and just said, fill in the bond requirements given the arrangement of the atoms. So this becomes, I think, even simpler. And I'm just reminding us, hydrogen needs 1 bond. Carbon needs 4 bonds. Oxygen needs 2 bonds, 2 dots. Knowing those basic rules, we can start to connect these structures very quickly. In other words, I know that I've got to first of all connect all of the atoms with a single bond, right? They have to be at least attached by a single bond. Now, when I look at the hydrogens, they're done. This oxygen can get its 2 dots and 2 bonds by adding 2 more sets of lone pairs. And to get this carbon to have 4 bonds, I can see that it requires a next bond and the 2 dots on the oxygen up above. We've satisfied every requirement. Carbon with 4 bonds, check. See how we did that? Here's the 4 bonds around carbon. Perfect. Oxygen requires 2 dots, 2 bonds. Oh, we got it there. And we got it here. 2 dots, 2 bonds, the oxygen requirement. And lastly, of course, each hydrogen has 1 bond attached to it. So just thinking about how easy that becomes when you let the periodic table guide you into the number of dots and the number of bonds, spending that critical time we did in the first lesson together. And so I think you have some opportunities to do that, in a little bit of your homework assignment as well. And this is interesting. Here's an example from your homework where you're actually given, a ball and stick model. and you're asked to convert that to a Lewis dot structure. And so really just understanding that the oxygens are in red, and if you're printed out in a black and white, it might be hard to tell, but the oxygens are the red. You know that carbon is always modeled with a black molecular atom there. And then, of course, the hydrogens are the gray or the white kind of molecular model kit ball there. So I would see, let's start here. That's a carbon attached to 3 hydrogens. And it's leading to an oxygen. That's where I'm at now. Which then leads to a carbon who's double bonded to an oxygen. That's this part. I can see that it's leading to another carbon. Oop, and there's a hydrogen. Double bonded to a carbon. Coming out as a hydrogen. Single bond. Double bond. Oxygen. CH3. So just by kind of following that all of these are oxygens, these are hydrogens, these are carbons, I'm able to just go through and connect the atoms. Now I want to carefully consider, especially for oxygen, I want to make sure it has 2 bonds, 2 dots. 2 bonds, 2 dots. And here's another set. And finally there, 2 bonds, 2 dots. Okay, we're back in action. I had to pause there for a moment. So here all of a sudden we've just had an opportunity to practice putting bonds and dots from a molecular model. And sometimes your homework is going to show some connectivity and just ask you to finish. And so I just wanted to share all the different varieties of homework type questions. And so for instance, in letter A, let me just model this one. I'm going to separate these so it makes a little better sense. I don't want all those atoms to come together. Letter A gives me 1 carbon, 5 hydrogens, and a nitrogen. And just ask me to draw the structure and make sure it's valid. So I'm just going to emphasize, here's what we know. Hydrogen, 1 bond, and it's done. Carbon requires 4 bonds, no dots. Nitrogen requires 3 bonds, 1 set of dots. And that completes the octet for each atom. So first of all, obviously, every atom has to be connected by at least a single bond. There has to be an attachment there. Alrighty. Now, what's left to consider? Well, hydrogens have each got their 1 bond. As a matter of fact, carbon has its 4 bond requirement. The only thing left to repair is the nitrogen. It has its 3 bonds, but it needs a set of dots. And that's all there is to that problem. Connect them, and then decide if anyone receives extra dots. Here's HNO2, nitrous acid, HNO2. I know the first thing I need to do is to connect everybody. Oh, you know what? This makes no sense. I am so sorry. That hydrogen, see how I did that? That hydrogen belongs to the compound below. No wonder it didn't make sense. I can't have 3 bonds on a hydrogen. On an oxygen. Let me redraw. H-O-N-O. That's all we were given in letter B. Got it. Okay, that helps me because otherwise I was breaking rules with oxygen. First thing we're going to do is to make sure everybody's connected by at least a single bond. I know oxygen requires 2 bonds, 2 dots. So I can satisfy this oxygen, 2 bonds, 2 dots, and I've satisfied this hydrogen with just its 1 bond. Right now, this oxygen and nitrogen don't have enough bonds. That lets me recognize there needs to be a double bond, a set of dots, and see what we've done there. Here's 3 bonds, 1 set of dots on the nitrogen, and I need to repair this guy. There's oxygen's 2 bonds, 2 sets of dots. And that completed the structure following the bonds and the dot requirements for each of our atoms. Let me clean it up just to redraw so you can, it's oxygen, nitrogen, then another oxygen. We completed everybody's lone pair just like that. Perfect. Letter C, C3H4. All right, so now I can see where I can attach everybody by at least a single bond. And then examine, have we met everyone's requirements? I noticed that this carbon, this looks good. It's got 4 bonds. He's happy. This carbon right now only has 2 bonds. This carbon right now only has 2 bonds. So that's not done yet, is it? All right, so if I look at that again and I see that hydrogens are good, this carbon here, we had a single bond. I know that doesn't make sense. That's my clue that we're going to need a multiple bond in there. And a multiple, to get each carbon, the 4 bond requirement will require a triple bond. So when I connect those atoms, each hydrogen only allowed 1 bond. Perfect. This first carbon has now 4 bonds. Perfect. But it leads out to a next carbon, leading out to a terminal end hydrogen. There's your structure that meets the bond requirements for each of those atoms. You're doing great. You know, just with any rule, there's always an exception, and I wanted to share a few of those exceptions and kind of look at section 4.3, exceptions to the octet rule. Well, most of the common elements are going to follow the octet rule. You know, hydrogen is a notable exception, and we've mentioned it all along, because hydrogen only wants to become like helium. Hydrogen will only have a 1 bond requirement, no dots. So technically it doesn't have an octet. It has a duet of a duet is 2 electrons, and then it becomes like helium. So since it has a duet instead of an octet, it breaks the octet rule. The other one I wanted to mention and already have earlier is boron. Since boron lives in group 3A, underneath boron is aluminum, but aluminum is a metal, so we know that metals will form ions. Boron is a metalloid and therefore will form covalent bonds. But since it only has a 3 bond requirement, it will break the octet rule. Boron, with its 3 valence bonds, has 3 bonds and 0 lone pairs. And that's okay, based on the number of bonds around it matching its group number. So this will be an octet rule breaker, but it's okay because of its group location. Sometimes elements in the 3rd row, and I just mean by the 3rd row is period 3 on the periodic table, they have empty d orbitals that are available to accept electrons. It allows them to expand their octet. So, octet, there I got it. Row 3 would include elements like phosphorus, sulfur, chlorine even, but phosphor and sulfur are very good at accepting more than their share of electrons around that octet. If I look at the phosphorus electron configuration, 1s2, 2s2, 2p6, notice now I'm into the 3rd energy level, 3s2, 3p3. The 3rd energy level does have d orbitals. We know that it has d orbitals, but they're unoccupied for the phosphorus element. But they're available to expand the octet. So when I think about where those electrons come from, I mean, this is the atom of phosphorus. How in the world can I get more than 8 electrons? Because here's this 2s, that's full. Here's the 3p3. I can see that there's 3 electrons there. It only looks like there's 3 open spots for bonding. And that's verified when I draw the electron dot configuration for phosphorus. There's only 3 open spots for bonding. But as an occasional rule breaker, phosphorus does have these open, unoccupied orbitals that it can use to put electrons in if it's asked to. It doesn't want to, but if it's asked nicely, it can expand its octet. Here's phosphorus in the center atom. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I look at all of those electrons around there, you can see 5 bonds, which really represents 10 total electrons. That's definitely breaking the octet rule. And how it does so is by placing some of these electrons in the unoccupied d sublevel. They're open and available for bonding when needed. Sulfur can do the same thing. Notice around the sulfur atom, and this is just kind of looking at sulfur, I see that it only wants to form 2 bonds. It's got 6 dots. But if it's made to, it can form up to 12 electrons, which is 6 bonds around the sulfur atom, because it has open d orbitals. Now remember, period 2 has no d sublevels. When I write a configuration 1s2, there's no d sublevels. Period 1 will never be able to expand its octet. Oops, and in the second energy level, we said that we had a 2s2, 2p6. That's it. Since there's no d sublevel, before we reach the third energy level, there's no chance that a second row element can ever break the octet rule. So it will never break octet. That was an N. In other words, it won't have more than 8. So when I say break the octet rule for more than 8 electrons. Now, because boron clearly broke the octet rule, but it was not going over 8, it was going under 8. It had 6. By the time it formed 3 bonds, only 6 valence electrons. So it doesn't break the rule, but what I'm referring to is period 2 has no ability to expand and go over 8 electrons. It has to be a period 3 element or greater to be able to even do this. And really, we're not going to focus too much on rule breakers. We're more focused on just saying that it happens, and if it does happen, it's because it has d sublevels. Glyphosate is the compound widely used in weed killer and is the active ingredient in Roundup. Add lone pairs and all the nitrogens and oxygens to complete the octet, part A. Okay, so we're good at that. We know nitrogen, who lives in group 5A, wants 1 set of lone electrons and 3 bonds. Oxygen, who lives in group 6A, 2 sets of dots, 2 bonds. So I can complete the dots on oxygen and making sure that it has 2 bonds, 2 dots. I can do that very quickly on each oxygen, making sure I set 2 dots. We got it. 2 sets of dots for each oxygen. Do that for the nitrogen. Here's one. 2 sets of dots, 3 bonds, it's perfect. We added all the lone pairs on the N and the O. Done. Letter B. How many electrons surround phosphorus in the given structure? Well, here's phosphorus, and I'm going to just encircle all of the electrons around the atom. How many bonds? 1, 2, 3, 4, 5 bonds. Well, that's the same as saying 10 electron. 10 bonds is 5 shared pairs. And that's a total of 10 electrons. There's 10. That's a rule breaker, isn't it? Which atoms in this compound do not follow the octet rule? Well, clearly that's the phosphorus. That's the skill level of recognizing rule breakers. Boron, he's a rule breaker with only 3 bonds. Hydrogen, he's a rule breaker. only one bond. Recognize that phosphorus or sulfur or other larger atoms have the ability to break the octet rule. You don't have to predict when, but if you see it, just know that it's okay. It's acceptable because they have their empty d orbitals to expand and allow more bonding around the central atom. When drawing Lewis dot structures for polyatomic ions, what we're looking at here now is, well, I think, let's just pause. Okay, I just paused that video and want to apologize because I wanted to be sure that I had your notes filled in before I took a next new step. And so I'm just looking at the bottom of page 4. When I was going on and on about expanding the octet rule, I wanted you to know that I asked you to draw the structure for phosphoric acid, just to stress that we know that phosphorus was breaking the octet rule. But I neglected to call it phosphoric acid, but I wanted you to see that this is the structure you drew in there. And that when I asked you to draw the structure for sulfuric acid, that you saw that this was the structure you drew in there and recognized that sulfur was breaking the octet rule. Then I worked this example problem where we put in all the valence electron dots on the nitrogens and oxygens and recognized that phosphorus was breaking the octet rule. Then we're ready to go on to talk about polyatomic ions and drawing its valence shells. But then pause this video here and render it and pick up with a new video looking at section 4.4. We're going back and practice how to draw electron dot structures for polyatomic ions. But let's take a break and come back when ready.